Hi, AP Calculus students. How you doing? Welcome to the kitchen. We're going to be doing notes 5.3 on my writing tablet. And let me go ahead and share my screen. There we go. Already got it set up to go. Just going to pull myself probably about right there. Okay. So for section 5.3 notes, I just really didn't feel like I could fit it all on my whiteboard and I didn't want to squish everything in. And so I have this note sheet and we're going to go ahead and fill that in. I also put this note sheet on Schoology in case you want to print it, right, or follow along. So 5.3, you have seen before. It has inverse functions. So when you did your review for chapter 5 that had exponential logarithmic, you also did a review of how to write inverse functions. Okay, so we are doing obviously the calculus part. So it's kind of cool in chapter 5. Again, like I said, we do derivatives and integration together. And we're only doing really parts of the sections because we already looked at a lot of them on when we did a pre-calculus review a while ago. So let's look at the calculus part of this. So number one, how do I use calculus to prove a function has an inverse, which is monotonic, or meaning one-to-one, meaning for each x there's only one y, and for each y there's only one x. And the reason why we care is a function for each x there's only one y. Excuse me. So if we're going to go ahead and write the inverse and we want it to be a function, which we prefer, for each y, there has to be only one x in the original function. Okay, so when would this happen? When would a function be monotonic or one-to-one, where for each x there's only one y and for each y there's only one x? Well, this would be if a function is only increasing or decreasing on its domain or on a domain that's given to you, meaning its derivative would only be positive or negative. Think about it. Think if you're running a marathon and you are continuously running. When you are done, if someone had a printout for you, for every time there would be a new distance, and for every distance there would be a new time because your distance was always increasing. So we're going to use derivatives to see if functions have inverse functions. So let's take a look. Does f of x equals x cubed plus 1 have an inverse? Well, if you graphed it, right, you would see that it does pass a horizontal line test. You know what x cubed plus 1 looks like. So yes, its inverse is a function. But what else could we do to check that using calculus? We can actually take the derivative of the function, which is 3x squared. And notice that except for where x is 0, this derivative is always positive, right? Think about the function x cubed plus 1. Isn't it always increasing as x's increase? Meaning that it does have an inverse function. Yes, it does have an inverse function, right? The key word is actually kind of function right there. Okay, let's look at B. Does f of x equal 2 sine of x from 0 to 2 pi have an inverse? Well, if you graphed 2 sine of x from 0 to 2 pi, you would see it doesn't pass a horizontal line test, right? Let's use calculus to show that that is true. So let's take the derivative, and that would be 2 cosine of x. And notice from 0 to 2 pi, right, that there are times, right, here's the from 0 to 2 pi. Notice in the first quadrant, cosine is positive. In the second, it's negative. In the third, it's negative. And in the fourth, it's positive. So from 0 to 2 pi, the derivative does change sign. It increases and then decreases. So this is no inverse function. Notice that monotonic, mono meaning one, right, would be one direction, either increasing or decreasing. Now, what we're going to be doing is finding derivatives of inverse functions, usually using only the original function. not writing the inverse. Why would we want to do that? Sometimes it's very difficult to write the inverse, but it turns out that it's a pattern that you can actually see yourself. So what we're going to do is we're going to have a function, we're going to take the derivative, we're going to write the inverse function, take the derivative of that, and then let's see how is the derivative of a function related to the derivative of its inverse. So let's take a look at number 2 here. So at number 2, let's find the derivative of the function. Obviously, that's a -7, right? Now let's write the inverse. Okay, this gives me some room up here. I know how to write the inverse, right? I'm going to make my f of x y, and here's -7x plus 2. I am going to switch the x and the y. And then I'm going to work to get the y alone, and that will be the inverse. So I'll subtract a 2 and then divide by a -7. And we could split this up, and in fact, I will. So the inverse would be that's an equal sign, a -1/7 x plus 2 sevenths. Okay, so here's the inverse function right here. All right. Now they want the derivative of the inverse function. Notice that's a -1/7. Okay, so how is the derivative of the original function related to the derivative of the inverse function? Let's take a look here. They are reciprocals of each other. It would appear. That's an S. Reciprocals of each other. Let's see, let's try that with x cubed. And let's see in a point and see if that holds true. Okay, so given f of x equals x cubed and a solution point of 2, 8, right? Notice that 2, 8 is a solution point to x cubed. Find the derivative. Okay, that's easy, right? We already did 3x squared. And then let's evaluate that derivative at 2. So that would be a 12. Okay, now let's find the inverse function. I'm sure if you did that, you would discover, and because there's only one function going on, that the inverse, guess I didn't really need to write that, is the cube root of x, or x to the 1/3, right, would be the inverse function. Right? And so, and now we're going to find the derivative of the inverse function on C. So let's bring, I meant to give myself more room, I think. Let's bring that over here. The derivative of the inverse then there we go, is I'll bring the 1/3 out front and multiply it and reduce the exponent by 1. That's a -2/3. I will put that in the denominator as a +2/3. There we go. So there's the derivative of the inverse. And now let's evaluate that derivative at 8. So you may say, well, why am I using 8? I used 2, right? Up here when I found the derivative of the original function. Because take a look. The solution point of the original function was 2, 8. And if we wrote the inverse, switching the x and the y, that means that the input for the inverse must be 8 and it outputs a 2. Notice that's true. When you put an 8 into 8 to the 1/3 is 2, right? So that is why, because we wrote the inverse, we are using and evaluating at 8, the inverse point. So let's take a look. When we put an 8 in, that would be, we have 1/3, and that is the cube root of 8 is 2. 2 squared is 4. Look at that, we get 1/12. Now, well, now I'm just writing anywhere, aren't I? So D, how is the derivative of the function at 2 related to the derivative of the inverse at its inverse point? Again, it would appear they are reciprocals. Same sign, right? Not opposite reciprocals. It would seem that they are reciprocals. So we now see what the rule is. What do we do though? It's easy to get confused because here's what's going to happen. We are not going to be writing the inverse. We are going to be finding the derivative of an inverse function using the original function. That's what's going to be going on in the book. And that's what's going to happen on the AP exam. So let's go to number 4 here. The derivative of an inverse function. If g of x is the inverse function, then the derivative of g is, take a look here, the reciprocal of the derivative of the original function evaluated at the inverse point. Right before, when we evaluated the original function, we evaluated it at x. So when we are evaluating the inverse point, that would be at where we switch the x and the y. Okay, so how do you find the derivative of the inverse function at the input of the inverse function when you've only been given the original function? So just so you know, even as a calculus teacher, when I do this, I have to, when I see it on the AP exam, I have to straighten it out in my head. Okay, let's read the steps and then I'll say the steps. A, find the derivative and see if the inverse exists, right? We have to do that first. Since A is the input of the inverse, right here, or again, they're calling g of x the inverse, then you will be using f of x, and you will be using f of x to find the derivative of g. You have to set the function equal to a. Again, let's go back. Because they're asking you to find the derivative of the inverse function at a, that means we have to set the original function equal to a to find the x that we are going to use in the original function. We have to inverse the points, okay, to find x, the input of f of x and the derivative of x. Okay, C, then find the derivative of f at its input x that you just found and write the reciprocal. This is the derivative of g, or the derivative of the inverse at x equals a. You found the derivative at its inverse point without actually writing the inverse. You will see 1 or 2 of these problems on the AP exam. So as soon as you see an inverse sign, the inverse symbol, the -1, this is what you'll do. So again, just so it's, because that's pretty confusing. So here's what I do when I'm on the AP exam and I see an inverse function. I go, okay, number 1, I'm going to find the derivative of the original function they give me. Number 2, I'm going to set the original function equal to the a value they give me. And I'm going to get that x. Number 3, I'm going to evaluate the derivative of the original function at that x. Number 4, reciprocal. Okay, so here we go. So example 5, find the derivative of an inverse function if a equals 2, that's the input of the inverse, and f of x equals x plus 3 over x plus 1, where of course x can't be equal to -1 because the denominator would be 0. Now, let me just point out to you, can you write the inverse of this function, and take the derivative of it? Yeah, but what a pain in the butt, right? Take a look here. This f of x you would make y, right? And then you would switch the x's and the y's. Now you have x equals y plus 3 over y plus 1. And now you have to get the y alone. That's a pain in the butt. So let's just find the derivative of the inverse function at its input using our original function. So we don't have to write the inverse. Here we go. Number 1, let's find the derivative, right? We're using the steps above. Again, as soon as I see this on the AP exam, I almost look away and run these steps through in my mind, 1, 2, 3, 4, so I can have a clear path because it gets confusing. Okay, the derivative, quotient property, the derivative of the numerator is 1 times the denominator minus, I'm going to keep my numerator and multiply it by the derivative of the denominator, which is 1, all over the denominator squared. I think we can clean that up a little bit. Let's see, the x's would cancel right in the numerator when I distribute that negative, and I have plus 1 and a negative 3. So I have negative 2 over x plus 1 squared. Notice that this derivative is always negative, meaning that it has an inverse function, right? Take a look. The numerator is always negative. The denominator is always positive because it's being squared. There is, its inverse would be a function if I were going to take the time to write it. Okay, step 2. Just trying to make this scroll up. It doesn't want to. There we go. Step 2, take the function, the original function, and set it equal to the a value they gave you. That is the input of the inverse. So it means then that it is the output of the original function, right? So I have to find the x's where that happens. Okay, let's multiply both sides by x plus 1. Right, so when I do that, I'll get 2x plus 2 when I distribute the 2. Okay, some quick math here. That means that my x would be, let's see, I'll subtract an x. My x would be 1. Okay, what's my next step? Bring those two things together. Evaluate the derivative of the original function at the x that you just found, right? Bringing it all together. See, when I put a 1 in there, that would be 2 squared for a negative 1/2. My last step is to take the reciprocal, a negative 2. This value, in fact, here is the derivative of the inverse function evaluated at its input, negative 2. So always set these steps in your head very clearly. I hope I was able to help you. And when you do section 5.3, just keep it really clear in your mind. Find the derivative of the original function. Make sure it has an inverse function. It will, right? Set the function equal to the a value they gave you. Find the x where it happens. Bring those two things together. The derivative evaluated at x, then take the reciprocal, and you'll be good to go. Have a good day.